Welcome. This is going to be a little bit of a tutorial. We're going to talk about how to create a simple classifier, and we're going to use the X-rays. I think it's actually really kind of nice using actual images. You can actually get a real good feel for how classifiers work, and we're going to start with the Ultralytics Yolov8 model, and then we're going to fine-tune that model on images of knee X-rays which have no arthritis, like this image, and have severe arthritis. So we're going to try to create a classifier. Now, the original Yolov8 model would not be good at doing this since it's really just trained on ImageNet, just general images. And what we're going to show is how to take that model and fine-tune it based on your specific domain. And you can kind of, once you've gone through this Colab, which I have a link below my GitHub that you can use, you'll be able to use this same Colab for any images you want. You can look at brain images, or you could look at chest X-rays or ultrasound or whatever, and just kind of learn how this works. And it should be fun. So we're actually looking at arthritis. This is severe arthritis, and this is going to be no arthritis. No arthritis is actually a lot of space between the bones. This is just an X-ray. That's actually where the cartilage is. It's nice and clean. So, and this one you can kind of, it's pretty obvious. You can see here's the X-ray of the knee, and look at this, just bone on bone. That's going to hurt. There's no cushion. So osteoarthritis is also known as a degenerative joint disease, or wear and tear arthritis, a condition where the cartilage that cushions the ends of bones is gradually worn away and leads to pain, stiffness, and reduced movement. It's the most common type of arthritis and often develops slowly, typically in middle or older age. So when you're young, typically you have, this is really beautiful here, you got a nice knee, you got nice cushioning there with the cartilage, which you can't actually see on X-ray, but you see the nice bone. And then unfortunately, as you do get older, as we all get older, at some point, some of us are going to get osteoarthritis, which is essentially just bone on bone. There is no cushion, and that's just going to give you a lot of pain. So there's a special grading scale that's used called the KL scale by radiologists. None of us are. So this is definitely not a course in radiology. But just to get an idea, these in the X-rays can be graded in a scale from 0 to 4, where 0 would be no radiographic evidence of osteoarthritis, and 3 and 4, you're going to have both osteophytes, some joint space narrowing, some sclerosis. In severe disease, you're going to have large osteophytes, large joint space narrowing, sclerosis, and definite deformity of the bone ends. So you're like, this is kind of right there, because I'll show this more images where you'll see the deformity. But in order to make things very simple, I just want to have two separate classes we're going to look at, and we're actually going to combine grades 3 and grade 4 into one class, and then grade 0 is going to be no arthritis. So I have enough images and have a relatively reasonably balanced data set. It's a little bit easy to do. So there's going to be two classes here, 0 and 4 star. I'll call 4 later on, where 4 star is really the combination of class 4 and class 3 and class 4 osteoarthritis. So that's just to make things easy. You will definitely, as you play with it, you can kind of do anything on your own as you want. In the beginning, I'm actually going to have all these images are going to be loaded up onto the Google Colab, which I'll show you how to do that a little bit later. But you want to mount your drive. This line just mounts your drive. This line is going to be using to import the Ultralytics library. And then this part of the code is going to be to actually load the model. We're going to be using Yolov8n-cls.pt. If you want to know more about that model and how it was created, you can go ahead and go to the Yolo site on the Ultralytics website. Now this is just the vanilla model that comes in. It's kind of, you should definitely play with this, try different images that you have online and see how it works. Just see how this code works. I've taken a yellow car here. I've taken this, fed this into the model, and then the results are what are printed out here. This is what the results are, what the model says it looks like. So you have an image, that's the image source, you put it into the model, boom, pops out this content here. It's giving you a 0.5 for being a cab, 0.17 for being a wheel, and then 0.12 for being a beach wagon. So play with that and see how it works, just without any fine tuning. How does this thing work on? You can put any image that you want in there. So it's a really, really easy to use, and so I encourage you to play with that. Now we're going to take this model. This model has not been trained on X-rays. We want to fine tune it and have it become a classifier. And it's going to be a very simple classifier. We're just going to classify two different types. Basically, no arthritis, or what I'm calling severe arthritis, which is a combination of classes 3 and 4. In order to take all these images, you need to find them. You can actually find them online. They're easy to get. If you go to either to Hugging Face or to Kaggle, there's probably many other places you can find X-rays online. Go ahead and download those and then put them onto your drive. Make sure you follow copyright rules, and if you need to delete those images, go ahead and do that after you're done. But go ahead and do what you need to do. Find whatever images you can find, and you don't have to even use knee X-rays. You can use anything you want. This is just an example using knee X-rays. But you want to make sure you put them in your folder in the specific way, which is a way in which they're read out by the training when you train your model. So you want to put all your images into a single folder. In my case, I put it in the single folder knee-XR-2. This is the path to that folder. And inside that folder, there are going to be two folders, both a train folder and a test folder. And in each folder, there's going to be sets of images where there's going to be no arthritis, which is going to be folder 0, and there's going to be arthritis, which is going to be folder 4. Do that also for your test data set and your train. And then we're going to run our model here. Now, I did a relatively simple exam where I'd use about 175 images, which are in the training set. 175 images in the training set which have no arthritis, and about the same that have arthritis, and also about 35 images in the test data set with arthritis and then without arthritis. And it's good that you'd like to want to balance the arthritis and the non-arthritis. If you don't balance your your training data, you're going to have a little bit of a trouble in getting a good model to come out, but you go ahead and play with that. I got an okay model, not great, but okay. I think probably been a lot better if I'd used more images. And then when you train your model, we're going to use the Yolov8 model and train it using this command here. And we're going to freeze a certain number of layers, freeze 9 of the layers inside the Yolov8 model, and then we're going to fine-tune one of the layers, the other layers. This is a very common way of fine-tuning, and you'll kind of see this. So if you understand how to do this, you will understand how to fine-tune just about any other models. Kind of happens in the exact same way. You have to choose how many epochs you want to go through. I went through 200. You can change it to 5 or 10 or 30. I'd probably use lower number of epochs initially, as you want to kind of play with the data set and see if it's working, and then you put more epochs in there and see if it works any better. So let's go ahead and take a look and see what happens if we run this. This is just some code that's been run already. As you can see how it goes through each epoch here. There's 1, 2, 3, and it goes through all through 200 epochs here. You can see this column here is the accuracy. Accuracy is 0.5 when it comes initially, and it's going to get better and better as we go down. And the losses also should be improving too. We'll go through that. If you go all the way down here, it looks like the accuracy is getting better, but it's still not that great, but it's okay. I think let's see what it does at the very end. I think it stops down here. It looks like we're getting 0.76. I have some images of that. So once you've trained your model, you can use this command to create your new knee model. So knee model is now the new model that we're going to use to see how that does, to actually look at true images of X-rays and see if it can figure out whether there's arthritis or not. Okay. So I'm going to try out this model on some X-rays. Now it's important to use images when you want to test something out. You want to use something that the model has not seen at all. So that model, when we train it above, has not seen these X-rays at all. So I have a separate folder called knee final exam, and inside that I have a set of images without arthritis, which is in 0, and with arthritis, which is 4. And you'll have to kind of create that as well to test it out. And once you've done that, basically run this code and let's see how it does. So here we go here. Let's see here. So the first one it got wrong. This is actually one that should be, well, let's see, what do we say here? Yep. This is supposed to be all cases that have arthritis. This is pretty obvious. There's arthritis here. This is almost bone on bone. This should have been a class 4, but it guesses class 0, so that's not good. This one also it kind of missed, so yeah, it's not very good at all, huh? Okay, well, it looks like it got this one 4. It got, missed that one there. It looks pretty bone on bone. That's not very good. How did it do here? It kind of missed this one here. Okay, what did I do here? Let's go back down here. Okay, yeah. So it's doing, I would say, not so great, but we'll do a calculation later to tell you how it does. This one it did pretty good. It hit that one. I still think it's doing a little bit better than 50-50, although it doesn't really look like it, huh? But I think a little bit better than just flipping a coin. So you go through here, it kind of does much better towards the end here. These are all being marked as arthritis. This one it kind of missed. Missed that one too. Got that one right. Got that one right. Let's see how it does on cases where there is actually arthritis. And, you know, it didn't do that great, so maybe we'll have to kind of play with it, probably to get more images. Maybe look at the individual training set. Maybe the individual training set is not very good. But that's part of what doing machine learning and modeling is. You have to sort of play with your model and make it a better model, and this is how you learn. But unless you actually look at the raw data, I don't think you can actually tell what's going on. Now, how about this? This one, it said class 4. Well, it should really be no arthritis. It's actually the other data set, which there's no arthritis. As you can see, when you run this code, it's going through all the images here which have no arthritis, which is 0. Okay, so these all should be predicting class 0. The confidence level is 0.529, so it's not that great confidence, but it should have been 0 there, so that's wrong. This one it got right. This one it got right, 0. This is 0 too. Hey, it's doing much better now, 0. So hey, it's actually much better at predicting this class, it seems. This one it kind of messed up on. You kind of can go through here and see. So how do you quantify this? So if we go down here, you can kind of see what's happening. Let's actually look at the original model. I'm not if you want to see how it did actually on the model, this actually comes out of the Ultralex platform, and it actually can. We're actually going to do some of these calculations, but it actually show you the loss. So as you go over more and more epochs, the loss. Remember, if you kind of you should be understand that when the loss is getting smaller, that's better. So losses were high initially. That means your model was not doing very great. And as we trained it more and more, losses were getting better, but it kind of peters out here. So it's a question why it's not improving, and so you kind of have to look at that. You can actually look at the accuracy also, and the accuracy started out like at 50%, which is like pretty much like tossing a coin, and it got better up to like 70, 80% looks like. So it is improving, which is definitely better than it was when it started, but it's still obviously not perfect. Now the way you can quantify that is using what's called the confusion matrix, and from this confusion matrix we can actually calculate the sensitivity and specificity, accuracy, and the positive predictive value. Okay, so basically what this confusion matrix says that if true is what the actual case is, this means no arthritis. So if there's no arthritis, how did it do on, this is actually on the test data set, not on the one that we gave it, that was earlier. So if you put in something that has no arthritis at all in the test data set, it basically 28 times said there was no arthritis, and 2 of the times it kind of messed up. Okay, you'd like to have in this confusion matrix everything in the diagonal and nothing on the side. So it's actually doing pretty good over here. Over here, if you put in something where it's definite arthritis, 23 times it says it has arthritis, and 10 of the times it kind of messed up. So it's not doing very good in this on this side when there's arthritis, which you kind of noticed above, but a little bit better when there's no arthritis. So how do you quantify that? Well, you quantify that by putting in the true positive and true negatives and do some calculations. You can calculate the accuracy. The accuracy is basically the diagonal components here, which is the true positives, true negatives divided by the total, and it looks like there's 81%. So that's actually, I'd say, reasonably good accuracy. The sensitivity is the true positive, or the true positive or the false negatives. It's about 70%, and the specificity actually is much better. It's 93%. So it's actually a relatively specific model. Specific basically means that there are fewer false alarms. There are very few true negatives, so this number is very small. So When it says that there's no arthritis, you can be pretty confident there isn't arthritis, but it's not very sensitive, so it's kind of not picking up a lot of cases. And so there may be this model will probably work okay in situations where you need very good specificity, but it will not be very sensitive. And its positive predictive value is actually 92%. So the specificity is high, but sensitivity is not so great. You can kind of, I would recommend, playing with this data set and seeing, maybe change the number of epochs, maybe load up different images, maybe get even more images, maybe don't do the thing that I did where I combined grades 3 and 4 into one and see how that does. Maybe try different classes, maybe something easier. I actually had a bunch of pictures of flowers that I took outside of my neighborhood. It's springtime when I'm making this video, and I actually did really good with that. So it may just be better at doing certain things, and probably flowers are in the original ImageNet data sets, which is probably why I did better than these. And so I really encourage you to play with this. Hopefully this is helpful for you, and it teaches you how to really just use a simple vision model and how to fine tune it and then create a classifier. And I found this really appealing, so you can see real images and kind of see how it does, and it should be pretty easy to use. So thanks for listening, and hope you have a good day.